Hey everyone, it's Norm from Tested here, and we are on location. We're going to a location for a shoot today, and I think it hopefully is gonna be a cool place. One of the technologies we've been covering at Tested for the past decade is the emergence of drone technology, like hobby RC drones, from companies like DJI. And alongside that fast-paced development has also been the question of when we might see drones in commercial spaces for things like drone delivery. One of the companies working on drone delivery is Google with their spin-off Wing. We saw a few of their prototypes at Maker Fairs in years past, but I didn't realize they actually have been making drone deliveries today. They're actually in the field, in places, in cities in Australia and the East Coast in the US, shipping people coffee, lunch, Tylenol, you name it. Where we're going to today is one of their test facilities south of San Francisco, where they run their aircraft that they've developed to make sure it's safe and to test the platform that they've developed. And we're gonna hopefully check out that aircraft, learn about the prototypes that got them there, and check out what it means to have delivery not in a 2-day window, same day delivery, but in a same hour delivery time frame. So hopefully a little bit of that future that we've been promised. So now here with Adam Woodworth. Adam, we've met before. Yeah. Tested viewers actually may recognize some of your projects that have gone viral, some of your RC personal projects, but your day job, you are the CTO of Wing.
Yeah. I've been involved in aviation my whole life, and whether it's on the hobby side or on the professional side, I just really like flying things.
And designing things
to
fly,
designing things to fly.
And here you're designing, you and your team have worked on many iterations of the design that have now are now in the field. That's a thing that blew my mind. You guys have not only at this facility done the tests, but people are getting real deliveries. So I want to kind of hear about from the technical side and the aircraft design side, how you got to this point. And where did you start?
One of the main drivers here is at the forefront, sort of the safety of the operation. So when you're flying things, you really want to make sure that those things are reliable, they're safe, they have a low impact on the community you're operating over. And so most of the design elements on this system were sort of built to meet that goal. If you look at this plane, sort of as an aircraft designer, this isn't sort of what I would normally think of as like what a plane should look like, but it really is the outcome of all of those design constraints. At the most fundamental level, we're basically like if you took a normal multi-rotor quadcopter and sort of smushed it together with a regular airplane. So we can take off vertically, hover like a helicopter, and then these rotors up front will turn on and we accelerate up to sort of flying speed. The hover motors turn off and we can cruise efficiently on the wing there.
And that VTOL design gets you the benefits of that vertical takeoff, so you can deploy not necessarily with a big runway, and you take advantage of all the modernization of the electronic speed controllers, the things in the drone world, the RC hobby world, but also the efficiencies of when you're flying fixed wing.
Yeah, so the wing lets you go further, farther, faster. And the hovering system lets you get into, it lets you sort of drop off a package in somebody's backyard where you wouldn't, we wouldn't be able to sort of come in and circle and land. The other element of this is that you're basically carrying around a spare airplane with you all the time. So if you think about, I'm flying around as a plane and one of these servos breaks or one of these motor breaks or a part of the tail breaks, you have a whole second airplane with you, so you can slow down, hover like a helicopter, and you sort of have implicit redundancy in the configuration.
Are both systems operating ever at the same time? Like when it's in a glide mode, are you using the rotors that are for the VTOL?
So under normal operating conditions, they sort of operate independently. So once we get up to cruise speed, the whole hover system will turn off, and then all of your roll, pitch, and yaw commands will come from these aerodynamic surfaces. There's an interesting period between when you're hovering like a helicopter and flying like a plane, where all those things have to be working together. But one of the benefits of having this sort of configuration is that you have a very over-actuated robot. So like if you think about you have these 6 degrees of freedom you can move around in, and normally you have sort of actuation degrees of freedom. You have 12 hover motors that can all generate forces. You have 4 cruise motors that can all generate forces, and you have 4 control surfaces that can all generate forces. So there's a sort of a very interesting and complex allocation problem here of let's say this control surface isn't working,
Right.
you have a bunch of other actuators on the system that could sort of lend a hand to make that happen.
Right.
And that's sort of one of the underlying philosophies of our whole design is this sort of like graceful degradation of performance if you have any sort of fault. So let's say this breaks, or you have a motor that breaks, or you have a sensing problem. You want the system to sort of gracefully adapt to that degraded condition and sort of just keep just keep operating.
And that's just a natural benefit of the design of going for a VTOL design, which sounds like something your team knew you wanted to do at the beginning. But like you said, configuration isn't what you would normally think of when you as an aircraft designer. But going back to like your earlier prototypes, that looks like a traditional fixed wing. So is this where you started?
Yeah. So this is one of the places we started back in around 2014, and this was called a tail sitter design. So basically the hover system is the same as the forward flight system. So you take off in this orientation, and then to go into cruise like an airplane, you tilt over 90 degrees and accelerate out.
Well, you lose some of that redundancy.
But so some of the issues here are you don't have that sort of inherent redundancy in the configuration, and you also have to size this propulsion system for both cruise and hover efficiency. So like those are from an airplane design perspective, those are very different sort of performance regions. The requirements for a hovering system are usually much different than both the power requirements and sort of the efficiency trades that you have when you're cruising. And so for a configuration like that on the VTOL side, where you have a sort of separate lift and thrust setup, you can optimize each one for their relative environments.
And then that transition part, that's where the
and
magic happens.
Yeah, and one of the sort of other benefits of going to the configuration we have now is the transition event is one of the sort of more dynamic events in VTOL flight. So for something like this, you have to pitch over 90 degrees. All of your the sensor sort of orientations change. The orientation of the package changes. It's a relatively dynamic maneuver. For a configuration like we're flying today, you more or less just sort of accelerate. So if you think about it, you have sort of like an infinitely long runway now that's up in the sky, and the plane can just sort of it can take its time to get up to speed.
Where we're going, we don't need roads.
Yeah, and there's no you don't have to change the orientation of the GPS antenna. You don't have to worry about is the vision system that's helping with navigation, does that need to change orientation? And for a lot of the things that we're carrying, a lot of it is prepared food. You don't want want your coffee cup to have to do a 90-degree coordinate transform.
Or build in something like a gimbal storage system. And to go from there to this configuration, is it simulations in CAD?
A lot of it, I always joke the way that you design airplanes is spending a lot of time, drawing all the airplanes you're never going to build.
Yeah.
So you really do sort of, go to the whiteboard, and everybody sort of puts up their Post-it notes of like, well, what if it looked like this? What if it, had 50 rotors instead of, 12? What if it changed shape? What if you had multiple airplanes? Like there's all these, you sort of fully explore the design space, and then you start applying some of the operational constraints to it. So, an example of that would be like, okay, well, we want the package to maintain a fixed orientation. So you can take a bunch of the concepts you've drawn, and then you can sort of push them off to the side. We want redundancy in hover, so you can take a lot of the components that can't absorb a propulsion system failure, you can push them off to the side. And eventually, just sort of on first principles, you can narrow down the design space from something that looks like there's thousands of options into just a handful that you can go and do sort of the deeper math trades on. Like for this system in particular. A lot of the design work was around, having the margins to be able to absorb system failures. So if you think about a regular camera drone, like a regular quadcopter, if you lose one motor, it's very hard to maintain sort of attitude and roll, pitch, and yaw control. For something like this, if you lose one motor, you have a bunch of other motors to make up for it. But there are some combinations where, even if you have 6 motors, you might be able to lose one and still maintain steady level flight, but you can't complete the mission. We found in a lot of the design trades, the sort of reliability case closed around 8 motors. So 8 hover motors would be sufficient to absorb a propulsion system failure, or sort of
50% more here. That's a good sweet spot.
And the interesting trade that we discovered was you're designing sort of primarily to the safety and redundancy target, but then since you're offering a commercial service, cost is a large element, and sort of general complexity of the build becomes a large element of it. And by going from 8 up to 12 motors, you can shrink the size of the motors, so you can use less expensive materials for the lift rotors. Like these don't have to be carbon fiber; they can just be plastic. It also moves you into a size of motor that's much more popular in the hobby space. So you have the sort of volumes of production scale there that affect the cost there. And in our case, the smaller rotors, we don't have to position align in any particular orientation. So if you had a big rotor on here and you wanted to stop it to hover, it's acting like a little wing.
Yeah.
And that can cause a lot of drag, and that can also sort of make the controls problem harder. So by going from 8 up to 12, it let us shrink all the individual propulsion system elements, and in many ways, like, be able to ignore some of the second order problems.
And then you described this as having like 2 flight systems in one, basically 2 airplanes in one physical design, but then you're also carrying a payload.
Yep.
And a payload that's not attached to the body, it's hanging right at a set length, the determined length with a package. Can you talk about how that factors into the flight characteristics and the design of this?
Yeah, so this box in of itself is a sort of very interesting design case study. So where the airplane on its own is about 4.5 kilos, and the package is about another 1.5 kilos. So a third of this weight is in here. So if you look at sort of normal payload fractions for a hovering thing, that's a lot of weight to be carrying around. And it's also relatively big compared to the airplane. Like, if you look at this, like the size of it compared to the wing, this is a lot of surface area to be dragging around. For all those reasons, we went to an external payload, so that if you think about it, if you size the fuselage to carry this inside, you carry that drag throughout the whole flight. In our case, like, we're dropping off the box. So if you carry it on the outside, you only need to take that drag penalty on the way there, and you can fly back as a sort of cleaner, smaller airplane. But carrying it on the outside makes this sort of part of the airplane.
Right. With all the vector forces.
Yeah, so all the loads that all these other parts of the plane have to take, this has to take as well, and this also can't impart sort of any strange forces on the plane. So everything about sort of the shape of the box, the construction of the box, is all to address that. And if you look at it sort of from the front, it forms a relatively aerodynamic shape, not a super aerodynamic shape, but relatively so. And because we don't control the orientation that it goes up into the bottom of the plane, it needs to be symmetric, so that, like, if you design this nice sort of aerodynamic body one way and then it locks the other way, you might have some problems. Additionally, the assembly of the box needs to be relatively straightforward. This is part of, as we sort of partner with merchants, as we carry other folks' goods, this is like part of their operation. So they're having these things at the restaurant, somebody's got to put it together. You got to make sure that when you put it together, it will still fit into the airplane. It can't take up a lot of space. So there's an interesting sort of paper folding problem associated with all this, of how do you get this shape to fold flat, to fold open, to be rigid when it's connected, and to fit up into the bottom of the airplane.
It's a combination of aircraft design and packaging design in one.
It's a very interesting one.
So I'm here with Tony, who's a flight test engineer who runs the flight testing operations here. Tony, this is where you and the team have been running tests nonstop for the past couple months to get certification from the FAA. Is that
That's
right?
right. That's right. We set up this facility actually about 1.5 years ago and spent most of 2020 preparing for type certification, which required us to do over 1,000 flight hours and multiple cycles with our aircraft system here. And so this was set up to help facilitate that. And then earlier this year, we operated the system through the end of the type certification requirements, and were able to produce the outcomes that we wanted.
So what I saw earlier today was an example of what would have been going on with the aircraft landing, taking off, having the packages that were sent, to 1 kilometer away or so, which is that representative of what a deployment in the field looks like? If, in Australia or Virginia, where you have this, is it somewhat like this with these pads that are for charging, but also with these giant QR codes? Is that what it is?
It is. It is. While we don't have residential neighborhoods around here, we've designed this to be as representative as possible. So the distances that we have, the infrastructure that's in place, a lot of this mimics what our situation looks like in the production environments in Australia.
So this is 50 aircraft, but it could scale, right? It could be smaller, it could be bigger. There's space this much apart. Give me a sense of what that cycle looks like. What is this aircraft doing now, and what does it do, in that cycle of takeoff and landing?
Sure. So it's obviously on the charging pad right now. This is where it's being charged up, the batteries that are inside the aircraft. And then once a customer places an order, the aircraft receives a mission to begin its delivery mission to this customer. And so it'll take off from the charging pad. It will go and meet the merchant at a specified location where the merchant loads the package onto the aircraft. The aircraft then travels to the customer's front yard, backyard, wherever it may be, delivers the package, and then returns home to charge again.
Wow, so up to 2 stops, right? Going to a merchant with a operational range of how many miles or kilometers?
We're looking at 10 to 15 kilometers or so.
Okay, so that's pretty good. And also that gives you a sense of like distance from merchant to a user, an end user,
Right.
of like what type of speedy delivery they're looking for, right? The same half-hour delivery time frame. And it's charging for how long, typically?
Charging depends on how far it flies. So if it does a very short mission, then obviously charging time is less. But generally, we're looking at anywhere of 10 to 30 minutes or so.
Wow. And at this scale, like I think the thing that we're bearing lead is it's all autonomous, right? Like you have people watching the computer systems that run this, but the missions are sent via backend, and up to these 50 of these aircraft here are all independently going on those missions.
That's correct. And it's really strange to think about this because as the pilot in command, you're responsible for all these aircraft, but you're not actually flying them.
Right.
And so being a manned pilot, switching into the autonomous space was a bit of a shift that took a while to get used to. But now that we're here, it just makes a lot of sense. It's much safer. It's much more efficient. And ultimately, I think this is the way that we scale these types of operations.
Is there any way to directly tap into these aircraft for direct RC control? No,
So for the production operations, which would be in our business environments, there's no way to tap into the aircraft itself. We're here at a test facility, so we do have some extra capabilities here. And some of our aircraft, you may have seen, have a little RC receiver on them. And that is for if we need to do any type of overrides while we're doing specific test campaigns.
And then kind of how aware are these aircraft of each other? Are there sensors on them that allow them to know what's around them outside of just the fiducial markers, or is it all telemetry?
So there are some sensors on board the aircraft that allow it to understand the world around it. It could see trees, it can see obstacles, but when it's in the air, it's not aware of other wing drones as it's flying, and all of that is managed by our backend system where it's able to plan all the different routes and keep everything deconflicted.
That sounds like that's one of the big technology hurdles, is creating that flight controller system, what would be an air traffic controller, but for a scalable number of drones.
Yeah, and actually I had my undergrad in air traffic management, and so it's really cool to be in this space where commercial aviation has manned traffic, air traffic control, where here it's fully autonomous. And you could imagine a world where maybe our air traffic control system could expand and potentially provide benefit to other airspace cases.
So Brandon, tell me a little bit about the way these aircraft are controlled. What's the system like that runs them?
The system, when someone orders something, the system takes that order, and when the merchant is ready to load the package, a flight path is automatically created. So our systems take into account the aircraft's capabilities, the geospatial knowledge in the flight area, any airspace restrictions, or any other limitations in the exact flight area, and a 4-dimensional path is generated. So that's 3 dimensions in space, and then the other dimension is time.
Right.
And those volume reservations are like the contract between the unmanned traffic management system and the airplane. And the airplane flies within that reservation volume to deliver your package. And all these reservation volumes are actually usually unique. Each order creates a custom plan that's optimal for that time and place to get that package to you.
And that's taking into consideration everything else going on in your system.
Yes.
What other flights, the things that may need to get prioritized. You're saying there's information that's hard-coded in terms of maybe geography, is weather or something that's factored in?
Yeah, we take into account the weather and the winds because the airplane does fly an airspeed to deliver the package. So depending on if there's a headwind or tailwind, those timings could be different, but we take all of that into account.
And getting to the point where the system works, if you're taking like basically what a air flight traffic controller would be doing on their day-to-day job, but applying it to maybe these parameters for delivery.
Yeah, and it's fully autonomous.
Right.
And we've created the algorithms and the system to test and evaluate those algorithms is actually quite expansive. We do millions of simulations every single day, and we have other algorithms that can look at that data and look at the optimality of our software to make sure that if there's any issues, then we can fix them pretty quickly.
Is it fundamentally a closed system in that it's your aircraft information that it's factoring in, or are there external other telemetry that you're also considering?
We've built the system from the ground up to be interoperable with other unmanned traffic management systems. So in the industry, there's a drive towards having these service suppliers that can supply unmanned traffic management solutions. Right. And we have the capability to share those four-dimensional reservations with other systems so we can all deconflict together.
Is that a trend that industry is moving toward? Like,
yeah.
We see this, I see it working reliably right now for delivery, but is that not just scalable number of aircraft, but size and type of aircraft? And this fundamentally, this type of system is how the skies will be kind of traffic controlled going forward.
Yeah, exactly. We really view drone delivery as a new form of transportation. And I think there's going to be many, many use cases that we haven't even contemplated. And we all need to be able to share the airspace together to really bring this new form of transportation to everyone.
We think of traditional delivery services using vehicles, right? They work on existing infrastructure. There's an understanding between community and and government and regulation of what that is. Here, it's a lot of new ground or air, right? So what is that like to work with different countries or different communities?
Yeah.
And having them understand that airspace becomes part of that delivery experience.
Yeah, I think there's I think that the way that you framed it is, it really is a new thing, right? So it's a new bit of that infrastructure, and we try to really respect that, right? Like, you're introducing something fundamentally new. You don't want it to be disruptive. You want it to be additive to the experience. So we do a lot of community outreach before we go into an area to offer the service. We do a lot of sort of surveying of the folks who are the relative few on the planet who are getting to sort of experience this in reality. Like, the feedback of sort of what people are experiencing is really important. It helps feed into what the next versions of stuff like this will look like. And I think generally, I always look at, like, reality is the ultimate cure for the what ifs. So when you have an industry, you have a technology that the idea of has existed for so long, like, there's a lot of time to imagine all the things that might happen. There's a lot of time to sort of plan out all the scenarios of like, oh, well, this is what it'll look like, or these are the risks, or this is what scaled operations will look like. But once you actually do it, like once you actually go and see it in operation, all of that becomes clear. Like, you start to see sort of what the real trends are, where the real risks are, where the real risks aren't, and it lets you sort of fundamentally reframe the problem.
So I'm sure one of the questions people have is, when is this going to be in their part of the world? Where does this make sense? Where do you, as a company, think this makes the most sense? And what does deployment look like when you reach places outside where you're testing currently?
Yeah, so you've seen the test site today, but this is a reality for a number of communities across the globe right now. We've got operations in 2 cities in Australia, in Finland, and on the East Coast in the U.S. And the delivery experience is, for an average customer, it's not that much different than any of the other sort of on-demand delivery services, where it's just sort of become a part of their daily life. So we've got a little marketplace application. You pull it out. You say, hey, I want this coffee, or I'd like this. We sell a lot of full roast chickens. I want this chicken, and you go through the checkout, and unlike unlike a regular delivery service, we present a couple of different options for, where would you like the box delivered. So, it'll say, it'll look at a bunch of constraints around, what the aircraft needs to be able to, sort of get from the environment in order to drop off the box. But basically, if you've got about a 10-foot diameter circle somewhere in your yard, the plane will be able to go and leave the box there.
So it's not like predetermined group share drop-off points. It really could be
really
GPS based, your backyard.
Yeah, it's totally sort of like a zero infrastructure solution, and in many ways like a sort of a planning-free solution. So if that bit of your property happens to meet those set of constraints to get the plane in, the plane will come and it'll come drop off your box, and the whole experience might take 30 or 40 seconds, and the plane's gone, and you've got whatever the thing is you were interested in getting. We're doing right now. There's on the order of like a flight every 30 seconds or so somewhere on the planet where somebody's getting that reality of drone delivery. And the cool part for me is I've liked aviation forever, but aviation is a somewhat rare experience, right? Like you think about when was the last time you flew on a plane?
Exactly.
A lot of people you remember the first time you flew on a plane. If you ask somebody the same question about when was the first time you drove in a car, it's like automobiles have been like fully normalized. Like it's just part of sort of the day-to-day life. And the cool part here is that we're doing the same thing with aviation. Like you're taking that experience of aviation, which was previously a very rare experience, and it's like for those pockets of the globe right now, it's part of the everyday. And I think it's a great way to introduce people to aviation. It's also like it's offering a pretty valuable service that in comparison to any other form of transportation is fundamentally better for the environment, fundamentally safer. We target levels of safety for moving the box as being literally safer than any other way you could move that box. So, compared to picking up the box and walking down the sidewalk, like having the drone bring it is actually like a net increase in the safety of the whole ecosystem. And so it's cool to see, having spent the majority of my career in this space, it's cool to see it starting to become a reality in these parts of the world. And our hope is that those parts of the world expand, and there's more places where people are experiencing this, and that's why we're continuing to refine the capabilities, we're continuing to build out the test infrastructure, and really trying to sort of prove at all levels that this is something that makes sense, this is something that is safe to operate, this is something that is sort of a net positive wherever we happen to bring it.
Thank you so much, Adam, and your team for inviting us out here to check that out. It's really amazing what you guys have done and to see how far it's come since we started seeing glimpses of these at places like Maker Faire.
Yeah. I remember it was probably 3 or 4 years ago now. I remember showing you all around a plane that didn't really look like this yet.
And no one could talk about it. No one could
and
say
we couldn't say anything about it. But I think one of the cool things is that you can go on YouTube right now and you can see videos that are like shot by customers, like people who are actually experiencing it. It's sort of outside of that demonstration space now. It's starting to become a sort of real part of everybody's lives.
So that was really, really neat. And I think the thing that was maybe the most surprising was just how much it all just kind of worked. I mean, the fact that this is a technology that they've been working for the past 10 years has gotten to a point where it's out in the field, and you can get, standing in the middle of that deployment facility, 50 aircraft launching and landing, was kind of like that, a little bit of that magic of technology that we love. A couple takeaways I had though. One, the engineering they've done into the aircraft, from the prototypes to what they ended up with, incredibly amazing. And the amount of thoughtfulness, things that I never thought or knew they had to consider, from the packaging design to even the hook, right? How it hooks onto the package. All of that seems to be stuff they've been really smart and iterated on. But maybe more importantly is that back end, that software and the algorithms that they've made, that platform for autonomously controlling a fleet of aircraft, doing the job that an air traffic controller would be doing, but on an airport that doesn't need to look like a traditional airport, a drone port that can be shipped in a shipping container and put up and remotely controlled over the cloud. That's going to be technology that's going to be not only essential, as I now realize, for drone deliveries, but also for any type of autonomous vehicles. When we think about the dream of flying cars or even airplanes in the future, could have applications there. And then finally, there's what Adam said at the end that really stuck with me, which is what they're doing isn't just, making the science fiction reality, the science fiction world a reality in the technology, but in the practice. And that's the most important part. As engineers, they can invent the technology to make this work from a technical standpoint, but none of it matters unless it makes sense and it's practical in the real world. And that's going to have to be a harder thing, I think, for them to get over. The communities accepting drones in the sky. I think they've already had feedback about what the drones sound like as they're flying and making these deliveries. Because when we think of drone deliveries, it's not just getting to remote farmers or to remote people who live off the beaten path, but they're talking about getting people real items in their backyards, and to make drone deliveries as common as your DoorDash or your Uber. And for that to happen, I think they still have a little bit ways to go in both the regulation and also in both in terms of the acceptance in society. But good luck to them, and thank them for inviting us out there to check out this tech. And as novel as it may seem to me and to you, their hope is that it becomes really commonplace.